Hi, George Diamond here. Welcome to my flipped classroom. This is AP Calculus. Today we're going to be continuing our look at differential equations. Let me put my coffee cup down and we're ready to get started, I think. Now in our textbook, this is section 6.2. We're going to be looking at a particular type of differential equation problems, growth and decay, and a specific type of growth and decay model. Right? So we've all seen, if you've taken pre-calculus, you've seen other models of growth and decay, but this is a particular type of growth and decay model we'll be looking at today. Now we'll look at several examples. We'll look at radioactive decay, some prediction type problems. We'll look at a couple of different examples. Now most examples we'll be looking at, most of them, not all, but you can find them in the Larson textbook. And then we'll kind of go through them and kind of explain them a little bit. But so we're looking at section 6.2, differential equations, growth and decay. Now the type of problems we're looking at today involves this right here. So this statement right here. It says when the rate of change of a variable y is proportional to the value of y. So if you got a quantity, right, and the rate of change of that quantity is proportional to the quantity itself, okay, we have a differential equation. Now we're going to write this as dy over dt. That's the rate of change of y with respect to time. Okay, is proportional to y. Now remember when you write a directly proportional statement here, okay, k is called your constant of proportionality. Right? So that's our constant of proportionality. So once again, the rate of change of y, dy over dt, is proportional to y. So we're going to write it like that. Now what I'm going to do today is that we're going to go ahead and solve this differential equation. Now my classes, we've already done section 6.3 in the Larson text. So we already pretty much know how to separate the variables. And again, y on one side, your x factors, negatives and constants on the right-hand side, integrate both sides. So my students have already done that. So I guess we're kind of going backwards in our textbook. We did section 6.3 first, and now we're doing section 6.2. But let's take this differential equation. I want to show you how we take this differential equation and we get that equation over here. So let's see if we can solve this differential equation for y. All right, so let me erase the part in blue here. And let's see if we can separate our variables. And let's see if we can solve this differential equation now. We should get this answer right here. Now, start off, let's multiply dt to both sides. We have dy now equals ky dt. Now remember, we got to get all of our y factors on the left. So we're going to divide this side by y. We're going to divide this side over here by y. So 1 over y dt, or dy rather, equals, now the y's cancel out, k dt. All right, now once we get our variables separated, so this is we got our variables separated. Now, if this were a problem on the AP Calculus exam, we would have 1 point. So typically in a differential equations question, you get 1 point for just separating your variables. Okay, now we're going to integrate both sides. So integrate both sides. Now the antiderivative of 1 over y is natural log absolute value y equals. Now the antiderivative of k, now k is just a number. Right, so the antiderivative of a number here would be kt plus your constant integration. Now on the AP Calculus exam, that would give us another point. So already we would have 2 points, so if you put the plus c in here. All right, now to finish solving this for y, we're going to raise both of these to base e, so it'll be e natural log absolute value y equals e to the kt plus c. That gives us c e to the kt. Right? That gives me an absolute value y equals c e to the kt. Now to drop the absolute value, typically, okay, this would be plus or minus c on the right-hand side. But keep in mind, now c is a constant, right? It represents just a number. Right? So it's all pretty much understood to be either positive or negative. Right? So c can be either plus or minus. So we just drop that c e to the kt. That's how we get this equation right here. Now we're only going to solve this differential equation one time. But keep in mind, when we work with this formula here, we're actually solving a differential equation. So we're working with a differential equation that has already been solved for a while for a particular quantity. Now today we're going to do about 5 examples. Also, now as you look at our exponential growth and decay model, so this is our model. After we've solved our differential equation, this is our model, and this is our working model. This is the one we're going to be working all of our problems with. So that way we don't have to keep going through the process every time we set up our differential equation to go through this process to just get that equation. So we're going to start our problems with this equation. Now, so we're going to skip this part right here. So you want to do this one time to kind of show you how it's done. All right, now, whenever you look at the exponential growth and decay model, C is the initial value. So this is your starting value. Now, so if you got a differential, some type of application problems, you know, you got 1,000 bacteria in a petri dish at time 0. Well, C is going to be 1,000. That's your initial value, your initial quantity, whatever. All right. Now, K is called your constant of proportionality. So whenever you work with this particular growth decay model, you have two constants that you got to find. So we got to find C, right, the initial value, and we got to find K. So C is easy to get pretty well. Also keep in mind about the exponential growth decay, if the constant of proportionality is positive, so if K is greater than 0, it indicates exponential growth. So if K is positive, it's growth. If K is less than 0, it indicates exponential decay. Right, so that's going to indicate decay. All right, now we've got about 5 examples. We want to go ahead and get to those pretty quickly here. So let me see if I can get this erased. There we go. See if we can get this erased, and we'll get on with our first example. So let me pull this down here. All right. There we go. All right, so there we go. So, example number 1. Now, we've got, I guess, kind of what we call a low-tech version here of a screen within a screen. So, I've got the problems already written out. So, let's bring up our first problem here. Right. Now, just keep in mind, if you're taking notes on this or whatever, you're getting the problem, you may want to go ahead and write the problem down now, because in just a minute I may have to take this problem down and finish working my marker board here. I don't have a whole lot of room. So to make a little bit of room, I may have to pull that down and take it off in just a minute. But let's take a look at our first problem. So example number 1 says the rate of change of y is proportional to y. So right away, that indicates a differential equation, all right? And the one that we just looked at. So now we're going to use y equals CE to the KT. We're going to go through the process of solving for y again. So we've already done it once, so we're not going to do it again. So now when t equals 0, y is equal to 2. When t equals 2, y equals 4. Okay, what is the value of y when t equals 3? All right, now we set this up. Think of this information here as a series of ordered pairs, if you will. All right, so you can actually do a t chart if you want to. T and y. So instead of x and y, be t and y. Now, so we'll start off. So when t equals 0, y is 2. So we'll list that as an ordered pair. Now you can do it on a t chart if you want to. Like I said, when t is 2, y is 4. And we're going to make a little prediction. It says, what is the value of y when t is 3? So given a time value of 3, what would our corresponding y value be? So we're going to, what we're going to do with each of these problems usually, we're going to write an equation, and we're going to use that equation to make a prediction. So this time we're going to predict the value of y when t equals 3. Now first, we have to write our model. Right? So we're going to write a model equation that's going to model the information here in our problem. So using our exponential growth and decay model, let's start off. Now keep in mind, as you look at this data here, okay, the initial data at t equals 0, this is going to give us C. Okay, the next data point we're going to use to get K. Because remember, there's two constants in the exponential growth and decay model here. C, your initial value, and then K, your constant proportionality. So we have to get both of those before we can really do anything before we can make a prediction with our equation here. So let's see what we get then. Let's start off. Now first of all, it said at t equals 0, y is 2. So that's going to give us our initial value. So we end up here with y equals 2e to the kt. Right, because remember what we said, C is going to be your initial value. So at time 0, we got 2, 2, y is 2, quantity of 2 or whatever. So y is 2, so we're going to put that in right now. Now, first of all, let me show you why we get, or how we get 2 here, right? Because if you look at that order pair, right, so when t is 0, y is 2, so you have 2 equals, I'm only going to do this once, so 2 equals CE to the k times 0, right? So if you substitute 0 in for t, and 2 in for y, you have 2 equals c e to the k times 0 is 0, e to the 0 is 1, so you end up with 2 equals c. Right, so that's always going to give you your initial value, right? So that's why, and now we're going to skip this step from now on, but I do want to show you this one problem, why we're just going to take the 2 and plug it in for c, right? It's going to be our initial value of our problem. So let me erase this. Let's go and finish solving this now. All right, now, so we use the first ordered pair, right, to get c. Now we're going to use the next point here, the 2 and 4 to get k. So now we substitute 4 in for y and 2 in for t, and we're going to get our constant of proportionality now. Right, so let's take the 4, plug that in for y. That's going to equal 2e to the, substitute 2 in for t will give us 2t. Right, so we'll substitute that in. Now we have to solve this exponential equation now for t. So start off with divide both sides by 2. That gives me 2 equals e to the 2t. Now to get t out of the exponent, we have to use we got to use the logarithm. So let's take the log to both sides. So log. So we're going to do natural log 2 equals natural log e to the 2t. Now remember, natural log e to the 2t is just 2t. So natural log e we can drop. All right, and that's going to equal natural log 2. Dividing both sides by 2, okay, we end up with 1/2 natural log 2 equals t. Equals k, I'm sorry, so it'll be k. So substitute in, we'll substitute in for t, so this will be k. And let's see, this will be k here too, so 2k. So 2k, so we'll substitute in, so for t, this will be 2k here, so we'll make that change here. So 2k, that's our constant proportionality, so there we go. All right, so let's see, we've got k. Now, if you had a calculator, you can go ahead and punch this up on your calculator, but I'm not going to right now, because remember now, our final answer, we're going to round it off to 3 decimal places. All right, so I'm going to leave this right here the way it is. If this is our constant of proportionality. If you round this off to 3 decimal places, it's going to give you a huge error. All right, so I would recommend that you keep this. Now, if you do punch it up on your calculator, you need to take it out, 5, 6, 7 decimal places, past your decimal. To avoid any possibility of an error, because remember on the AP Calculus exam, it has to be accurate to 3 decimal places. If it's not, we got problems. So let's take the 1/2 natural log 2, and let's go and finish writing our equation. So our equation becomes y equals 2e to the 1/2 natural log 2 t. All right, so this is going to be our prediction equation. We know that c is 2, k is 1/2 natural log 2, and like I said, you can check the decimal on that. Now we're ready to make a prediction now. So to make a prediction, when t is 3, let's take the 2, take the 3 and substitute it in for t now. So we have y equals 2e to the 1/2 natural log 2 times 3. All right, so we'll substitute that in. And our answer here, I've already done this, is 5.657. So 5.657. So if you have a good calculator, it will do that calculation there pretty easily. So this is our first example. Not really an application per se. This is basically, if you can imagine, a couple of points on a graph is what we're looking at here with this information. So let's try example number 2. So moving right along. And we'll just kind of quickly run through each of these. So that's our first. All right, let's take another example. I'll leave the ty up here. I think we're going to need it again here in a minute. So example number 2. All right, so let me go ahead and bring up our next problem. So let's bring up our next problem here. All right. Now this is an application involving sales. Right, so sales of a company. That says 4 months after it stops advertising, a company notices that its sales have dropped from 100,000 units per month to 80,000 units. If the sales follow an exponential pattern of decline, what will be the sales after 2 more months? This will be after 2 more months, I assume. So let's see, what are we getting here? So after 4 months, it stops advertising. We've got sales of 80,000, right? So it started off at 100,000, right? So it dropped from 100,000 to 80,000. So our first data point here would be 0, 100,000. So it started, so the initial value here would be 100,000, All right, so as we start our equation here, y equals CE to the KT. Okay, this will be y equals 100,000 e to the KT. All right. Now it says, okay, sales drop following exponential pattern decline. What will be the sales after an additional 2 months? So after 4 months, we're at 80,000 units. Right, now, once again, this is a problem that's in the Larson text. So if you have access to the textbook there, you can find this problem in the Larson text. Right, so after 4 months, we're at 80,000 units. After 2 more months, so this would be after 6 months. Okay, what would be the sales after 6 months now? So we'll make a little prediction. This is an application. So 4 months after it stops advertising, a company notices that sales have dropped from 100,000. That would be the initial amount, the initial value, units per month, to 80,000 units. That's so it'd be 80,000. Follows an exponential pattern of decline. So that means that we're going to use our decline, our exponential growth and decay decline model, right? Okay, what would be the sales after an additional 2 months? That would be after 6 months, I assume. So let's see. Now we're going to use this first point here to get C. That gives us C. The next one we're going to use to get K. And once we get C and K, we have our equation written. Also, keep in mind, now you may want to go ahead and write this down now, because I may have to take that off in a minute to finish the problem. So I may need a little bit of extra room on this. Some of these problems can get kind of long, so just for warning. All right, so let's see. As we set this up, then let's see. Let's go ahead and let's go and get K first. So let's take the 80,000 and substitute it in for Y. So 80,000 equals 100,000. Okay, e to the KT, so T would be 4, so that would be 4K. All right, so substitute 4 in for T. All right, so we have 100,000 e to the 4th K on the right-hand side. Now, as you divide both sides by 100,000, you divide this side here by 100,000, 80,000 over 100,000 is going to reduce to 8 over 10. Those reduce, it gives us 4 over 5 equals e to the 4K. All right, so 4/5 equals e to the 4K. Now, we got to solve this for K to get our constant of proportionality. So let's take the natural log of both sides. So natural log 4/5 equals natural log e to the 4K. And that gives us 4K on the right and natural log 4/5 on the left. Dividing by 4, that gives us 1/4 natural log 4/5 equals K. All right, now, we've got our constant of proportionality. Right, we're ready to write our equation now. So our equation, we call this our prediction equation, if you will. Okay, should be equal to, let's see, y equals 100,000 e to the, let's see, so y equals 100,000 e to the 1/4 natural log 4/5 t. Right, so I believe everybody can see that okay. Let me see if I can erase this for you a little bit. There you go. So this is our equation. This is our prediction equation. Once you get C and K, now we can use this equation now to predict either the time or the sales over at any particular time or sales. So let's see now. After 6 months, what would the sales be? So we're going to substitute 6 in for T. So 100,000. Okay, e to the 1/4 natural log 4/5 times 6. Right, and once again, just be careful. Make sure you get your grouping symbols and stuff here, so watch out. I got 71,500 units. 500 units. All right, so after 6 months, we have 71,500 units. Okay, that's how many units are being sold each month after 6 months. All right. Okay, let's try another example. Let me take this one out. So that's another application. This. Okay. And let's see now, problem number 3. All right. Okay. Let's try radioactive decay. We'll try a radioactive decay problem because these are usually follow an exponential pattern of decline. So now with this problem, number 3, it says 10 grams of plutonium-239 is released by accident. how long will it take for 10 grams of plutonium to decay to 1 gram? So how long will it take for 10 grams to decay to 1 gram? So let's go ahead and start us a couple of ordered pairs here. This kind of be able to visualize your data a little bit. So let's see, we'll set this up T. So T and P. So that'd be, P would be the amount of plutonium. So T and P, let's say. All right. So so let's see. So it's reached by accident. Takes 10 grams to decay to 1 gram. And let's see what else. So 10 grams to reduce to now also the half-life. You can go ahead and put the half-life on here also. So the half-life for plutonium is 24,100 years. So 24,100 years. I'm going to put that on here too. So the half-life of plutonium is 24,100 years. So we want to get that in our problem also. Right. So as we get started then, to start with at T0, we're going to have 10 grams of plutonium, right? Now let's see, what else can we conclude now from our problem? Now we're going to use our P equals CE to the KT. So we use our growth and decay model again. So the amount of plutonium is equal to CE to the KT over time. All right, so we start off at T0, we got 10 grams of plutonium. Now, think about this now. We're given we have the half-life of plutonium is 24,100 years. So after 24,100 years, think of how much plutonium we're going to have. How much plutonium is going to be left. Now, that's the half-life. So you think, now, if we start off with 10 grams at T0, then its half-life after 24,100 years, half of it's gone. So now we've got 5 grams left. Right? So we've got 5 grams left. So that we're going to use to write our equation with. Now let's see what our prediction is going to be. So how long will it take for 10 grams to decay to 1 gram? Right, so how long will it take? This time we're looking for time. How long will it take for 10 grams to reduce to 1 gram? Okay, so once again, if you're taking notes on this, you may want to go ahead and write that down now. I may have to take that off to give us a little bit more room. So as we get set up with our problem, our initial value, so P is equal to T 10e to the KT. Let's go and put the 10 in first, all right? So that's going to give us our initial value constant, if you will. Okay, now we got to get K. Now to get K, we're using 24,105. So substituting 5 in for the amount of plutonium, that's going to equal 10e to the 24,100. Let's see, K. So we're substituting in for T. Right. Now, to write our equation, we're going to have to solve this equation for K. So let's see what we get for our constant of proportionality. Divide both sides by 10. We have 1/2 equals e to the 24,100K. Just take the natural log of both sides. So natural log 1/2 equals natural log e to the 24,100K. And once again, we're going to drop the natural log e of 24,100K here. And natural log 1/2 on the left-hand side. Now dividing by 24,100, divide here by 24,100 equals K. And this will be 1 over 24,100 natural log 1/2. So this is K. Now once again, I'm not going to write this as a decimal. If you do punch this up on your calculator and round it off, make sure you take it out, maybe at least 4, 5, 6 significant digits. All right, so this problem here is going to be negative, so it'll be a pretty small number. So just watch out if you want to write this in decimal form. As a matter of fact, I'd write every single digit down just to be careful. Our final answer, we want to round off the 3 decimal places, but you don't want to round this number off too soon. All right, so if you don't have enough significant digits, it will knock your final answer way off. It'll hurt your accuracy tremendously. All right, so let's see. Now we've got K. Let's go and write our prediction equation. All right, so our prediction equation becomes. All right, so our prediction equation will be. Let's see, I'm going to have to set this down. So let me take this off here. All right. So our equation becomes y equals 10e to the 1 over 24,000 natural log 1/2 T. So this is our prediction equation, right? Now, given 1 gram of plutonium, now let's see if we can predict the time. So once we've got our equation written, now like I said, we know what C is, we know what K is. Now we can solve for either Y or T, no matter which one we're given. So this time, let's substitute 1 in for Y, and we'll have 1 is equal to 10e to the 1 over 24,000 natural log 1/2 T. All right. Now, to get T out of the exponent, remember we went to use a logarithm to get T out of the exponent here. Let's start off by dividing both sides by 10. All right, so 1 over 10 equals e to the 1 over 24,100, I believe it is. So 100 natural log 1/2 times T. All right, and I take the natural log of both sides, so natural log 1/10 is equal to natural log e to the 1 over 24,100 natural log 1/2 T, right? And that's going to give us 1 over 24,100 natural log 1/2 times T. And that gives us natural log 1 over 10 here. So our answer, we've got to divide, should be natural log 1/10 divided by 1 over 24,100 natural log 1/2 equals T. So if you got a good calculator, you're going to need it right now. So go ahead and punch this up. Now when I did it myself, I got 80,059 years. So take 80,000 and 59 years. All right, so T is equal to, this is our answer here. All right, so you got to go ahead and divide natural log 1/10 divided by K, and that'll give you the number of years. All right, so once you, keep in mind, now once you write your prediction equation, all you do is substitute in from there to make a prediction. All right, let's try, we're going to try 2 more examples. Let's try this next problem here. So get this one erased. So get this erased here. All right, so 2 more to go. So we bring up example number 4. Right, let's try this here. Let's try a problem involving a disease, right? The flu, right? So it's flu season right now in my part of the country. So the number of people with the flu at any one time increases at a rate proportional to the number of people infected. So right away, that's a differential equation. The number of people with the flu at any one time increases at a rate proportional to the number of people infected. All right, so we're going to set up my differential equation here, number 4. We set this up, so P equals CE to the KT. So P being the number of people infected. All right. If 1,000 people are initially infected and 1,200 people are infected 7 days later, how many people are infected in 12 days later? Right, so if 1,000 people are initially infected, so at 0, 1,000, so 1,000 will be the initial number of people infected. So let's do this over here. So P equals 1,000 e to the KT. So that gives our initial amount. And 1,200 people are infected 7 days later. So after 7 days, you've got 1,200 people with the flu. Right, so 7 days later. How many people are infected 12 days later? Right. So after 12 days, how many people have the flu? Now once again, we already got C. We want to get our constant of proportionality, and once we write our equation, then we'll make our prediction. So let's see what we get. Let's take the 7 and the 1,200, substitute in for T and Y, and we have 1,200 equals 1,000 e to the 7K. Right, now we're going to solve this for K. Divide both sides by 1,000 here. So divide by 1,000. Let's see, the zeros cancel out. That gives me 12 over 10, which is 6 over 5. That's going to equal e to the 7K. Let's take the natural log of both sides. So natural log of 6/5 equals natural log e to the 7K. That gives me 7K on the right-hand side. Natural log of 6/5 on the left. And I'm going to divide both sides by 7, so divide by 7. We have 1/7 natural log, 6/5 equals k. So that's our constant proportionality. Now once again, if you decide to write this in decimal form now, you're going to take it out at least 5 or 6 significant digits. Right, so as a matter of fact, I would just leave it written like this and just use this in your formula for k. So as we write our equation now, so as we write our prediction equation here, okay, we end up with y equals, was that 1,000? Okay, e to the 1/7 natural log 6/5 times t. So this will be our prediction equation. And now it's just a matter of making our predictions. So we're given time. We're trying to predict the number of people with the flu. So it's just a matter of substituting in now. So we have y equals 1,000 e to the 1/7 natural log 6/5 times 12. All right. So let's see how many people have the flu, and that would be 1,367. So y equals 1,367 people have the flu. So this many people have the flu. Okay, let's see. Let's try one more. We'll do one more problem, and then we'll finish up. So one more exponential growth and decay problem. So we'll erase this. Okay, so one more problem. Let's set this one down. Okay, let's pull up our next example. Can try this a little bit different. Let's start with a graph here. Pretty simple. Now it says on number 5 here, it just says find the exponential function y equals c e to the kt. So number 5, we're going to write our equation y equals c e to the kt. Okay, that passes through the 2 points. Right, so really there's nothing to predict here. Okay, we just have to write the equation. This ought to be pretty simple. Right? So just a matter of solving for c and k. So our 2 points here, our initial value is 0, 4, and the next is 5 and 1/2. So this should be a simple matter of just solving for c and k. So start off y equals 4e to the kt. So the initial value here would be a 0, 4. All right. And to get our constant proportionality now, let's see if we can solve for k. So this will be 1/2 equals 4e to the 5k. So substituting 5 in for t. So 1/2 equals 4e to the 5k. So let's see, let's divide both sides by 4. So divide by 4, that gives me 1/8 equals e to the 5k. Okay, take the natural log of both sides, so natural log 1/8 equals natural log e to the 5k. All right, that gives me 5k on the right-hand side, and natural log 1/8 on the left. So we have dividing both sides by 5, gives us 1/5 natural log 1/8, okay, equals k. So that's going to be our constant of proportionality now. So as we write our equation, this will be y equals 4e to the 1/5 natural log 1/8 t. Okay, or if you have the decimal version, I think I got the decimal version also. So the decimal version would be, what did I get? So y equals. The decimal version is y equals, so y equals 4e to the negative 0.416t, so negative 0.416t. Right, so once again, k is negative, and you can see you have the exponential decline here. You get your graph is decreasing from left to right, so 1/5 natural log 1/8 is a negative number there. Okay, so 5 examples of exponential growth and decay, several applications. We looked at a problem with a graph. So I think my students, we are just about ready to begin our homework now. So we've done a couple of applications. We've done a radioactive decay problem and the graphing problem. So hopefully we'll be in good shape. So let's go do our homework.